Welcome to this presentation on learning physical layer communication with quantized feedback. My name is Henk Wijmeers and I'm at Chalmers University of Technology. This figure shows a classic view of communication systems, where an information source generates messages which are converted by a transmitter to a signal which is sent over a noisy channel. The receiver should then convert the received signal back to the original message and deliver it to the destination. A meaningful question in this context is what is the optimal transmitter and the optimal receiver that minimize the message error rate. In a more modern context, the transmitter, the receiver, and the channel may be affected by nonlinear stochastic impairments. This makes it hard to find optimal transmitters and receivers. An alternative meaningful question could then be, can we design good enough transmitters and receivers? In particular, in this study, we consider the effect of limited feedback to accomplish this task. To solve these complex problems, people have turned to machine learning methods. We can categorize those into two different streams. First of all, we have those that rely on a generative differentiable model of the transmitter, the channel, and the receiver. In this case, we can apply centralized learning with an autoencoder. These ideas have been applied to both the wireless and the optical domain. In case there is no generative differentiable model, we can apply reinforcement learning with feedback. There have been different studies using perfect feedback, also one on noisy feedback, and in this presentation we will focus on quantized feedback. With this motivation in mind, I here present the outline of the remainder of this presentation. We start by presenting the system model under consideration, and then describe how data-driven learning of a transmitter and a receiver without a differentiable channel can be accomplished. Then we cover different ways that losses can be transformed in a reinforcement learning context, and then we apply this to learning with quantized feedback as well as bit errors over the feedback channel. I will then present numerical results and end with conclusions. The transmitter and the receiver are modeled as deep neural networks. Let us look at the figure. The transmitter, f tau of m, takes as input a message m and generates a complex number x. The transmitter is stochastic, so it also adds a perturbation w leading to a transmitted signal x tilde. Then there is the channel p of y given x tilde, which is unknown to the transmitter and the receiver and may not be differentiable. The receiver takes the observation y and generates a vector of probabilities which approximate the posterior distribution. From this posterior distribution, the most likely transmitted message is selected and fed to the destination. The learning of the transmitter requires feeding back losses from the receiver to the transmitter. So from the point of view of the losses, the receiver f rho of y acts as the source, and the transmitter f tau of m acts as the sink. The loss function we consider is the cross entropy loss. It depends on the transmit parameters tau implicitly through the expectation, and on the receive parameters rho as shown in the equation. Here, we don't send the losses directly over the feedback channel, but we quantize them. The function q quantizes the losses with q bits. These are then sent over a binary feedback channel, which can introduce bit errors with a probability less than 1/2. And then at the sink, there's an inverse quantization, which leads to the estimated loss L hat, which is then used for learning the transmitter. We show here that by introducing a function shown in the yellow box, f, that learning of the transmitter is possible even when we have only one bit per loss, and the bit error probability over the binary feedback channel is close to 0.5. Before studying the impact of quantization, we first look at a simpler case without quantization. Since our channel is non-differentiable, we cannot take the gradient of the loss function with respect to the transmit parameters tau. So we apply an alternating optimization approach, where we learn the receive parameters based on fixed transmit parameters tau, and then we learn the transmit parameters based on fixed receive parameters rho. For learning the receiver, we apply supervised learning. We send a number of messages and then compute the empirical loss function based on the mini-batch. In this empirical loss function, the expectation in the original cross-entropy loss function is replaced by an arithmetic average. We then compute the gradient of this loss function with respect to rho and perform a gradient step on rho. For the transmitter learning, we send data using a stochastic policy. This means we send complex numbers x tilde k sampled from a distribution. We choose this distribution to be a complex Gaussian distribution with mean f tau of mk, where mk is the kth transmitted message, and variance sigma squared p, which is a value that we can set. The receiver computes the cross-entropy losses per sample, Lk, and feeds these back to the transmitter. The transmitter then computes a gradient with respect to tau of the loss function, which turns out to be given by the expression here on the right. This is based on the policy gradient theorem. We have a summation over the samples in the mini-batch, then L hat k, which is equal to Lk if the losses are not modified, and then the gradient with respect to the transmit parameters tau of the logarithm of the transmit policy. Given this gradient, we perform a gradient step on the transmit parameters tau. This figure shows the histogram of the losses within a mini-batch over progressive iterations. The x-axis shows the per sample loss and the y-axis the distribution. At the first iteration, all the losses tend to be very large, so we have a kind of peaky distribution around a large mean. For later iterations, the losses tend to be more spread out, with some small values and some large values. After many iterations, the losses tend to be quite peaky and close to zero, with a few outliers. The conclusion is that the losses have a non-stationary distribution, which makes it challenging to quantize them. To help us quantize the losses, we apply something called loss transformation or loss shaping. The figure on the right shows on the x-axis the losses and on the y-axis different transformations of those losses. The blue dashed line is the original losses, so f of L is equal to L. The red line is called clipping. Here all the losses are capped to a value specified as beta. Clipping has been shown to be beneficial for learning. The second transformation is called baseline. This is shown in yellow, where we shift all the losses with a constant. The use of a baseline has been shown to reduce the variances in learning. The third transformation is called scaling, where we multiply all the losses with a constant beta. Here the constant beta is greater than 1, so the losses are scaled up. Scaling has also been shown to be beneficial for learning. So these three operations, clipping, baseline, and scaling, can be applied with different parameters beta to a bunch of losses without adversely affecting the learning performance and possibly even improving it. We can now go back to our original problem of quantizing the losses. If we have q bits available for each loss, we need to find 2 to the power q quantization levels to minimize the expected distortion d. Here, P of L is the distribution over the losses, and Q of L are the quantization levels. There are standard approaches to solve this problem. For instance, Lloyd-Max quantization, uniform quantization, and vector quantization. However, since P of L varies with iterations, every time we apply quantization, we need to share the codebook, so that both the source and the sink have a common idea of what Q of L really means. To avoid this, we make use of the special properties of losses, clipping, scaling, and baseline, so that we don't need to share a codebook. Our proposal is as follows. The source goes through the following 4 steps. Given the distribution of the losses at the current iteration, it applies clipping between a certain minimum and maximum value, which can be adaptive based on the distribution. For instance, that the lowest 10% and the highest 10% values of the losses are clipped. We then apply a baseline of value L min, so that all the losses are in the region 0 to L max minus L min. Then we scale the losses with this range so that all the losses end up into the range 0 to 1. And then we apply fixed uniform quantization with natural mapping to those losses in this range 0 and 1. The sink, which is the transmitter, receives these quantized losses and then just applies an inverse quantization, and it interprets all of the losses as being within the interval 0 and 1. We can now go back to our original problem of quantizing the losses. If we have q bits available for each loss, we need to find 2 to the power q quantization levels to minimize the expected distortion d. Here, P of L is the distribution over the losses, and Q of L are the quantization levels. There are standard approaches to solve this problem. For instance, Lloyd-Max quantization, uniform quantization, and vector quantization. However, since P of L varies with iterations, every time we apply quantization, we need to share the codebook, so that both the source and the sink have a common idea of what Q of L really means. To avoid this, we make use of the special properties of losses, clipping, scaling, and baseline, so that we don't need to share a codebook. Our proposal is as follows. The source goes through the following 4 steps. Given the distribution of the losses at the current iteration, it applies clipping between a certain minimum and maximum value, which can be adaptive based on the distribution. For instance, that the lowest 10% and the highest 10% values of the losses are clipped. We then apply a baseline of value L min, so that all the losses are in the region 0 to L max minus L min. Then we scale the losses with this range so that all the losses end up into the range 0 to 1. And then we apply fixed uniform quantization with natural mapping to those losses in this range 0 and 1. The sink, which is the transmitter, receives these quantized losses and then just applies an inverse quantization, and it interprets all of the losses as being within the interval 0 and 1. Given the proposed quantization, we can now prove 2 propositions. The first proposition deals with the assessment of the impact of quantization on transmit learning. As a benchmark, we consider the case where all the losses lie in the interval 0 to 1. Quantization can be modeled with the Boos-Gang theorem as follows. The quantized loss is a gain times the loss plus a perturbation Wk. This perturbation is uncorrelated with the loss. There exist standard expressions for the gain and the moments of the perturbation. We also introduce 2 notations for the gradient of the empirical loss. One term in the gradient and the empirical loss for the unquantized case is denoted gamma k, which includes the loss and the gradient of the log transmit policy with respect to the transmit parameters. We have also a quantized version of this, which is the same expression where we replace the loss with the quantized loss. We can then relate those 2 gradients in terms of their moments. So it is possible to prove that the expectation of the quantized gradient is equal to the gain times the expectation of the unquantized gradient. There is also a relation with respect to the variance. The variance of the quantized gradient is upper bounded by the square root of the gain times the variance of the unquantized gradient plus a correction factor times the trace of the Fisher information matrix of tau. From this, we can conclude that there will be a reduction in the convergence rate and an increase in the variance. These results only hold for large mini-batches, where the empirical average tends to the expectation. From this, we can conclude that transmit learning should be possible even under 1-bit quantization, provided the mini batches are large enough. Our second proposition deals with the impact of bit errors on transmit learning. In addition to the two empirical loss gradient terms that we had for the unquantized and quantized case, we now have a third empirical loss gradient term, gamma k superscript e, which involves L hat k. Remember, Lk was the original loss, Q of Lk the quantized loss, and L hat k the quantized loss with bit errors. We assume 1-bit quantization and a bit error probability on the feedback link less than 0.5. We can now relate the terms in the empirical loss gradient for the quantized case and the quantized case with bit errors through the following expressions. We see that the mean due to bit errors in the gradient is reduced depending on the bit error probability compared to the case without bit errors. We can also upper bound the variance of the gradient based on the variance of the gradient with quantization and two terms that depend on the error probability of the feedback link. The last term again depends on the Fisher information. So we see overall that bit errors lead to a reduction in the gradient, so we will make smaller steps, and the steps will have a higher variance. These results only hold for sufficiently large mini batches. What we can conclude from this proposition is that transmit learning should be possible under high error rates, provided the mini batches are large enough. And this is one of the main results of this work, that we can do transmit learning with 1-bit quantization and very large error rates on the feedback link. In order to support our claims, we have conducted Monte Carlo simulations. The code for our simulations can be found on this GitHub repository. For all our simulations, we used 16-point constellations, and we considered two different channels, a linear additive white Gaussian noise channel and a nonlinear phase noise channel inspired by fiber optical communications. In both cases, the transmitter and receiver were not aware of the channel and could not differentiate through it. We will show 5 results. First, symbol error rate as a function of input power. Second, a visualization of the decision regions that were learned. Then we show the impact of the number of quantization bits on the symbol error rate. The fourth figure will show the impact of the quantization on the convergence rate of the joint transmitter and receive learning. And the fifth and final figure will be the impact of the error probability on the feedback link on the total symbol error rate. In our first figure, we show on the x-axis the transmit power in dBm, or on the top line the SNR mapped from the transmit power. On the y-axis the symbol error rate. The bottom 3 curves relate to the additive white Gaussian noise channel, where in dash blue we have 16 QAM with a maximum likelihood detector. In red we have the learned constellation with the learned receiver without any quantization on the feedback link, and in green dashed lines the same but with 1-bit quantization of the feedback losses. We see that we have some small performance gain compared to 16 QAM due to the geometric shaping that is learned by the transmitter neural network. Secondly, we see that going from unquantized losses to 1-bit quantization of the losses leads to no performance loss in terms of symbol error rate. The curves on the top relate to the nonlinear phase noise channel. Again in blue is maximum likelihood, 16 QAM, where we see performance degradations for high transmit powers. The gain of shaping the constellation leads to the red curve without quantization. And then in green, we again have 1-bit quantization where we don't see any performance degradation compared to the unquantized case. So this result establishes that we can learn good constellations and good receivers with 1-bit quantization of the losses. This second figure shows the learned decision regions for the nonlinear phase noise channel. On the left, without any quantization of the losses. On the right, with 1-bit quantization of the losses. We see that the decision regions look largely similar. So again, despite only having 1-bit quantization of the losses, we can learn a reasonable detector. This slide shows on the x-axis the number of quantization bits used in the feedback link per loss, on the y-axis the symbol error rate. We show 4 different cases. The curve in red shows when we perform fixed quantization on the range between 0 and 10. We see that we need approximately 3 bits per loss to get good performance. With only 1 bit per loss, the performance is degraded. In green, we show a similar case where we perform fixed quantization in the range 0 to 4. We see some performance gain, but still we need approximately 3 bits to quantize the losses. The proposed scheme is in blue. Recall that in the proposed scheme, we perform clipping, baseline, and scaling to bring all the losses in the 0-1 region and then apply uniform quantization. We see that the performance is not affected by the number of bits that we choose, so we might as well just pick 1 bit. In a dashed orange curve, which is hidden below the blue curve, we show the baseline without quantization. So we don't lose anything due to quantization. This current figure shows the impact of the quantization on the convergence rate. On the x-axis, the training iteration index n, on the y-axis, the empirical loss function at the transmitter side. We have 3 cases. In red is the unquantized case, which leads to the best performance. In green is the case with 5-bit quantization, which attains almost the same performance as the unquantized case. So with sufficient number of bits, we have no effect on the convergence rate. With 1-bit quantization, we see that there is some penalty in the convergence rate, even though we converge to more or less the same value in the end. And this is in line with our propositions, where we show that quantization leads to a reduction in convergence rate, because the gradient steps will be smaller and the variances are larger. In this final figure, we show the impact of the bit flip probability on the feedback channel, P, from 0 to 0.5, on the symbol error rate of the final learned transmitter and receiver. We have 3 different cases which all converge to the same low symbol error rate when there are no errors on the feedback channel. Let's now focus on the blue curve with 1-bit quantization and a small batch size of 64. We observe that for large bit flip probabilities, let's say 0.45, we have a significant penalty in terms of the symbol error rate. This is because with small batches and a large bit error rate on the feedback link, we will make often incorrect gradient steps. When we increase the batch size to 640, we obtain the green curve. For the green curve, because of the large batch size, we can invoke our proposition, which tells us that we will make gradient steps with smaller magnitude, but in the right direction. We can expect that when we further increase the batch size, our symbol error rate will be further reduced. It is interesting to note that the case with 2-bit quantization and a smaller batch size of 64 leads to intermediate result. So the more quantization bits we have, the more robust we are against bit errors in the feedback channel. This brings us to our conclusions. We have seen that data-driven learning can discover good transmitter and receivers even over complicated channels which are hard to model. This includes, for instance, transmitter and receiver hardware impairments, as well as nonlinear stochastic propagation channels. In order to learn the transmitter, you need a feedback signal back from the receiver. This feedback signal can be quantized and be subjected to bit errors. Our main result was that feedback quantization, even with a single bit, and bit errors on the feedback link, even very close to 0.5, have very limited impact on the learning performance. Even though we've applied these principles to very simple communication systems, they can be extended to other scenarios, such as MIMO, multi-user MIMO, coded communication systems where the coding can refer to both the forward link from transmitter to receiver, as well as the feedback link from receiver to transmitter. Since the losses are so robust against bit errors, it makes sense to look into compression of those losses. And finally, we believe that the single-bit feedback links can be useful for performing multi-agent learning. Finally, I want to acknowledge the funding for this research through the Marie Curie Actions and the Swedish Research Council. For more information about this work, I refer you to our paper available on IEEE Explore. Thank you for your time and your attention.